Electromagnetic motor, Ryan Himmel and Nick Pride, Group 7B. This experiment was conducted to display the effects of electric and magnetic fields upon a copper wire. The specific question that was tested was, how does the different voltage/current amounts affect the rotational velocity of the motor? This was determined in rotations per second, or RPS, and the data was collected using a video camera, and the tracker software was used to analyze the rotations per second. The initial hypothesis was that the RPS would increase and as the number of batteries increased. This is because peak was IV, and the more voltage introduced into the system will increase the amount of power into the system, making the coil spin faster. Our hypothesis was correct, as the RPS went up as the number of batteries added increased.
Our models show the system schema, which has the batteries, the earth, and the magnets all acting upon the copper coil. The force is calculated by doing the cross product of the current and the magnetic field, shown by the right-hand rule on the right-hand side of the page. This cross product produces one magnetic force that acts upon the coil. The earth is also acting upon the coil through gravity. The next slide shows the physics connections, along with the main model of the system. The two different models that we have here are one where the wire is coated and one where the wire is uncoated. This is each half of the wire. When the wire is uncoated, we will have current flowing through the copper wire, or copper stand, into the copper wire, which will induce a force magnetic from the current times the magnetic times length times magnetic field onto the copper coil, allowing it to spin. When we do not have any current going into the wire, then there will be no forces, because the cross product will be the magnetic field times zero current. This will show that the wire coil will spin due to the momentum that is created from the initial force, and will not switch around like what would happen if both sides of the wire were shaved. The forces are represented by the small circles with X's and dots in them, the dots representing the force coming out of the page, and the X's representing the force going into the page. If both wires were shaven completely, then what would happen is we would have opposing forces acting upon the wire, allowing the wire to oscillate back and forth between the stands and not rotate completely around.
Our experimental design included the initial setup, which has us strip off the protective coating on one side of the wire before using it. If this was not done, then the coil would flip backwards because the current would be allowed to flow through both sides. Connecting the alligator clips to either side of the wood block setup, which has the copper stand on each side, permanent magnets were then placed at the center of the wooden block to induce a magnetic field on the wire. The batteries were then connected, which allowed a current to flow through the wire that was placed into the copper stands. This caused the wire to rotate, and these rotations were able to be recorded. 3 trials were conducted with 1 battery, 2 battery, and 3 batteries, each at 1.5 volts. Some limitations we faced during the experiment were the frame speed of tracker from our recorded data, because the coil spun very fast, and the fact that we didn't account for any resistive forces, allowing us to assume that V is directly proportional to I. Overall, the results showed us that as you increase the amount of batteries, meaning voltage which is proportional to current, power and the rotations per second increase. This confirmed our hypothesis we initially made. The graph displays this well as the trend line is increasing.
When comparing our motor made in class to a traditional DC motor, we can see that traditional DC motors use the law of conservation of energy to keep their motor spinning. They actually flip the current each time the wire revolves around 180 degrees. This allows the force to be constant the whole time and keeps the motor spinning without using the law of conservation of momentum. Our motor didn't use this and stripped 1/2 of the wire to use conservation of momentum to keep the wire spinning and flip each time.
In conclusion, by stripping only one side of the end of the wire, it causes the magnetic force to be zero and doesn't allow current to flow. From there, the momentum allows for the coil to flip over and continue in motion, where wire is shaved and current starts up again. More batteries or more voltage allow for more current and power, which then gives more rotations per second, confirming our hypothesis. Possible errors would be not accounting for resistive forces, and they could have miscounted spins during tracker due to the limited frame speed of the program. Our results were as listed, and then for future design, if we did this experiment again, we would try to get a camera that can record at a higher frame rate, allowing us to see more rotations more exactly.